Well, I'm Drew. I have a confession to make. I don't know how to solve a Rubik's Cube. I feel like I'm the only one. Oh, okay. At least one other person can't solve a Rubik's Cube. That makes me feel better. Okay, so my name is Drew. I'm a UI engineer at CrowdStrike. I'm also an author. I wrote a book about Vim about 10 years ago. It feels like a lifetime ago. And I'm around the place as Nelstrom. And I'm really happy to be here today talking about flaky tests. It's a topic close to my heart. So let's start by defining what is a flaky test. Well, here we have 3 tests. This one should always pass. This one should always fail. And this one does both. All right, it's like a toss of the coin. Which way is it going to fall? Who knows? Let's just see what that looks like in the test runner. All right, so the failing test fails, as expected. The passing test passes. The flaky test has passed this time. Run it a couple of times. It fails this time. Passes, fails. You get the idea. It's a toss of the coin. I've implemented this using math.random. So I'd advise you not to use math.random in your test assertions. And that's it, really. You won't have to worry about flaky tests. So, any questions? No, okay. There's a little bit more to it than that. I wanted to illustrate that randomness can lead to unexpected results. But it's not always going to be as easy to spot the source of randomness as this. Often randomness comes in disguise. So we're going to spend a bit of time looking for the ways that randomness can disguise itself. But before we get into that, I want to spend a little bit of time talking about testing itself and best practices, if you like. So let's open up list sort test. Now, imagine that you need to write a function. This could be its signature. You're going to pass it a list, and you're going to ask it to sort it by a field that you specify in another argument. So if you wanted to test drive this, you might start by building a list. Each object in the list has a name field, and it has a position field. And then you might have one test that calls the function and says sort by name, and then you assert that the objects returned are sorted by name. You might have another test that does the same thing, sorts by position, and you assert that it's coming back sorted by position. Let's take a look at this test. So list sort. There we go. Look at that. We have a passing test suite. Great. Let's move on to the next task. Actually, before we do that, how about we just have a look at the implementation? So I'm importing this function called listsort, and it's coming from a file called naive listsort. That kind of raises suspicions for me, so let's take a closer look. Okay, I think there's some more work to do here, okay? So this is a function that takes in some input, and it just returns it unchanged. All right, who's at fault here? Is the implementation wrong? Are the tests wrong? Well, it's both, isn't it? But if I had to lay the blame, I'd probably blame the tests here. They're not making us work hard enough. If we have another look at this original list, it's actually already sorted by name, and it's already sorted by position. The order in which the list has been declared is already sorted by in all of the dimensions that we care about. So we're making life much too easy. You don't even have to write any code to make this test pass. When you're writing tests, you want to be antagonistic. You want to make life difficult for the developer. You've got your testing hat on, you've got your developer hat on. When you've got your testing hat on, you want to be a really difficult customer. So here, we can make things a bit harder if I'm just going to select these 2 lines, and then I'll swap them. Now it's not sorted by name. I'll select these 2 lines, and I'll swap them. It's no longer sorted by position. It wouldn't be a Drew Neal tech demo if there wasn't some text editing wizardry, by the way. So, okay, now we have our tests are failing. And this is really just our cue to actually go and do the work and implement that functionality. And here's one I rolled earlier. It's in a file called listsort. There's nothing interesting here, really. It just does the job. It's nothing of note. But when we use that implementation, the tests are now passing. Red, green, refactor. That's the That's the advice. That's the test-driven development methodology. You start by writing a test that fails. You watch that test fail, and then you write the smallest amount of code that you can get away with to make it green. Once your test is green, you have the option, if you like, you can improve things. Keep the test green while changing the implementation. Preserve that behavior. That's refactoring. It's optional. You can apply that step when the time is right. And then you write another failing test. You watch that test fail. Then you write the smallest amount of code to make it pass. You go round the cycle again and again. That's the test-driven design methodology. And I want to stress that you want to start with red. You want to see your tests fail. Because if your test is green, but you've never seen it fail, then how can you trust that it truly is green? We've seen an example already where the implementation wasn't actually doing any work, and we had a green test. So you want to see your tests fail before you see them pass. Why do we write tests, anyway? We want to give ourselves a safety harness so that we can take risks. We can go out there, we can make changes, and if we break stuff, the test suite should let us know, and we can fix those problems rather than shipping broken code to production and waiting for our customers to yell at us. So if you trust your test suite, you can take risks. You want to test your test harness. You want to really trust your safety harness. And that's why you want to test your tests. You want to see them fail. Now, I don't want to be a total purist here. You don't have to write the failing test first every time. Life's messy, it doesn't always go to plan. But if you've missed that step, if you've never seen your test fail, you can easily address that. You can just find the implementation, comment out some lines of code, break it, check that your test fails. You've got to test your tests. You want to trust your safety harness. Now, when you find that you've got a flaky test in your test suite, there is, I think, a temptation to hope that it will pass again. Here we have a test that is going to pass most of the time. You might run this on Circle CI, on continuous integration, and you might see it 50 days in a row, it always passes, and then one day it starts failing. And you just think, why did it choose today? It used to pass. But which is better here? We've got a test that's half-half and a test that mostly succeeds. But the thing is, they're both flaky tests. The only difference really is the probability of how often it succeeds, how often it fails. And here, we've got one test that mostly fails, another test that mostly succeeds. Which one would you rather debug? Okay, if your test is succeeding almost all the time, then that rare occurrence where it fails, it's really hard to track down the root cause. But if you've got a test that's almost always failing, it's almost as good as a failing test, back on your red-green refactor cycle. So rather than hoping that your flaky test will pass, what I suggest is that you be methodical about this and you find a way to make it always fail. So if you're starting with a flaky test, try to make it fail every time. And then you just follow the cycle, make it green, refactor. I've worked with a lot of flaky tests, and I've noticed two categories that come up a lot. One is timing issues. Another is leaky state. And if you're really unlucky, you might be dealing with a combination of both. So in the rest of this talk, I want to go through an example of a test that fails because of timing issues, and an example of a test that fails because of leaky state. And in both cases, we're going to follow this methodology. We're going to take the flaky test, we're going to make it always fail, and then we're going to find the problem and fix it, get to a green test. All right, we're going to start with timing issues. Just bear with me while I get my examples up here. Oops. Okay. So here we have a template, and it contains a pre-tag with some source code inside it. Let's just have a look in the browser. That's what it looks like. my first thought there is, it'd be nice to have some syntax highlighting. So there's lots of libraries out there we could use. I've chosen highlight.js for this one. And it's really, really easy to integrate this into an Ember project. I've done it by creating a highlighter, by creating a modifier called highlighter. So this imports the dependency, and then when the modifier is called, it receives an element as an argument, and it applies the syntax highlighting to that element. So we can easily use this by, in element space, we'll say highlighter eager. Oops. I'll get to why it's called eager in just a moment. So now we're using the modifier, and now we have syntax highlighting. Let's just take a look at the source here. So we started out with a pre-tag that had an ID and a single class of JavaScript. And you notice highlight.js has added a couple more classes, as well as adding these spam elements within the child content. So if we wanted to test this, we could do something like visit the route, and then look up an element by ID and assert that it has this class applied. OK, let's find that test. Timing. OK, there it is. So we're visiting the route, we're checking that the class is there, and it works. So this is our kind of starting state. We don't have a, well, let's hope we don't have a, I said don't hope. Hopefully we don't have a flaky test. Now, one thing I don't like about this implementation is that we've got this static import here for a big JavaScript library, and by importing it statically, we're basically adding this to the bundle so that all of our users have to download this. And that inflates the size of the bundle. It's bad for performance. So I've got an alternative implementation here called lazy. And here, we're using dynamic imports to bring in the dependencies. So this dependency won't be included in our default bundle, but anytime we use the modifier, the dependencies will be fetched, and the code will run. And this is relevant to what Simon was talking about earlier as well. So let's switch this from the eager to the lazy. And it still works. We're still getting syntax highlighting. I don't know if you can see this on the big screen there. There's a flash. I actually recorded I've recorded a video of this. I've got a slow motion replay. Hopefully it's slow enough you can see that when you click the link, there's a moment where the text is black, and then the styles pop in. And if you also look at, in the network tab, look at the list of scripts. And when you're on the home page, there's so many scripts. But when you visit that route, a couple of other chunks are loaded. And that's fetching the dependencies. So we have to fetch the dependencies before we can actually apply the syntax highlighting. And we get this little flash of unstyled text. And we've broken our tests. OK, so how do we fix this? Well, to understand why this is broken, I like to think about a marble run. Now, here we've got this clever little device. It's like a splitter. You can put in 2 or 3 marbles, and it sends one to one side, another to the other side, and back and forth. Now, I didn't have time to build an actual marble run, so I drew one. So if we have a splitter at the top, imagine you put 2 marbles in, one right after the other. One goes to the left, the other goes to the right. Now, if I ask you to bet on which one finishes first, you can take a look at this marble run, and you'll see that one side actually has a slightly shorter track than the other. The marble has less distance to travel, so you would expect that that marble would finish first. Try it out, and that's what happens. Maybe if you try it another 10 times, there might be one repetition where it defies your expectations. Because that's the beauty of marble runs, right? They exist in the real world. The real world is imperfect. For some reason, one of the marbles might run slower, and it might defy your expectations. Now, earlier, we started with this example of a test where we were making things too easy. The natural order that the list was declared in happened to give us a passing test, even before we'd written the implementation. So we decided to be antagonistic and to make life harder. by reordering the list. And what I'd like to suggest here is that we can manipulate the probability of which marble finishes first by adjusting the track. You know, if we want a particular marble to finish last, we can give it a longer stretch of track so it has further to travel. Okay, enough playing with marbles. Let's have another look at the code. Now, use your imagination here, squint a bit, and try to imagine that the test is one track of the marble run, and the application code is another track of the marble run. We have two separate timelines. And just like the marbles on the tracks, those timelines are independent. Once a marble's on its way, it's not going to be influenced by the other marble. So beginning with our initial implementation, with the static import, there's no asynchrony to worry about. In our test timeline, we say, let's visit this route and then wait a bit. And that kicks things off in the app timeline. It loads the route, renders the template, and the highlighter, so the modifier applies. And then when we ask the question in our test, has this class been applied? The answer is yes, and we get a passing test. When we switch to the lazy modifier, we've added a chunk of asynchronous work. We have to wait for those scripts to download before we can actually apply the syntax highlighting. So it takes a little bit longer. We've added a little bit of asynchrony. I'm using these spirals, by the way, to represent like something takes a length of time that might be longer or it might be shorter. You don't quite know. So when the test timeline asks the question, has this element got the class applied, it's asking the question too soon, and the answer is no. Now, you can look at this and you can think, well, if we could just make the test wait a little bit longer, we could get the answer that we want, right? We could adjust the length of the track to produce the favorable outcome. And let's try that. So let me just rearrange these. I want to see this one, and I want to see this one side by side. Okay, so if I say, in the test, we're just going to await timeout, and we're just going to wait for half a second. Let's see. Okay, we've got a passing test now. It's a slow test, but it passes. I wonder if we can get away with a shorter delay. Let's try 5 milliseconds. Let's see what happens there. Right, that fails. We're not waiting long enough. We're being impatient. Just run that a couple more times. Oh, look at that. It passed that time. So this is flaky. Okay? We've kind of adjusted the probabilities so it's almost half-half. So we need to be a little bit more patient. We'll wait a little bit longer. Let's try 50 milliseconds. And that seems to pass. I don't know how many times I need to do this, but it seems like a solution. Well, I don't recommend doing this, and there's two reasons why you shouldn't do this. The first is that it slows down your tests. Okay, you want your tests to run as fast as possible. As your test suite grows over time, you don't want to end up with it taking 10 minutes or more. So you don't want to slow down your tests. But the other reason, really, is that we chose the number 50 here, and it works today, but it might not work tomorrow. This is still a flaky test. All we've done is alter the probability. It's slightly more favorable, but it's still flaky. It still might fail. It still might, rear its ugly head at the most annoying time on continuous integration. So I talked earlier about adjusting the length of the marble run. This is the let's hope strategy. Now let's try it. We'll take this out, and instead of adding a delay there, we're going to make the implementation wait. Time. We'll wait, let's make it 500 milliseconds. So again, we're altering the probability, and this time, for all intents and purposes, we've got a test that fails every time. And now it's much easier to actually diagnose the problem and find a fix and be confident that it is a fix. Now, up until now, we've talked about these two timelines as being independent. You set your marbles on their path, and they just do their own thing. They're not influencing each other in any way. But I think we need them to influence each other. I think we need to add some sort of connection between the two timelines. So going back to the sort of marble example, if we have one particular timeline where we want to make sure that that marble always finishes last, imagine that we put a gate in place. When the marble reaches the gate, it stops. The other marble just carries on, and when it reaches the end of its run, it trips a switch that causes the gate to open. And the marble we want to finish last carries on, and it finishes last every time. Okay, we've connected the two timelines. And the tool that we have that makes this possible in Ember is test waiters. So let's think about what happens when you call visit 3. We await visit 3. And I kind of glossed over this earlier, but there's a lot going on under the hood. First of all, we find the route that matches the URL. That route is activated. The model hook runs, which is asynchronous. The template renders, which is asynchronous. And then the modifier runs, which in one case it's asynchronous, in the other it's synchronous. Now, the model hook and the template rendering are things that are owned by Ember, and Ember controls these. And Ember has this built-in concept called settled, like settled state. And essentially, when you say await visit 3, the thing you're waiting for is a settled state. Here's that timeline again, trying to sort of visualize this concept of settledness. So this time I'm not glossing over the details. I'm saying we visit this route, the model activates, we run the model hook. That's asynchronous. While that's happening, we're in an unsettled state. And when it finishes, we're in a settled state. But immediately after that, the render phase kicks off, and we go into an unsettled state again until it finishes, and we're back in a settled state. And that's the thing that await visit 3 is waiting for. So at that point, it's safe for it to ask that question, has this element got the class applied? And we kind of get all this for free because, as I said, like the model hook and the render cycle is managed by Ember. The way my mental model, I think the details of settledness are quite complex, but my mental model is quite simple. Every time there is a piece of asynchronous work happening, I imagine there's a Boolean flag which indicates that something is unsettled until it completes, and then it's marked as settled. And you can have lots and lots of asynchronous tasks happening all at the same time, and it just takes for one of them to be unsettled for the whole global settled state to be unsettled. But once all of those pieces of asynchronous work are complete, this sort of global concept of settledness is now... oh, I got a typo there, sorry. The colors should tell the story, though. So this is now settled. It's true. Okay, so going back to this timeline, this is where we introduce the dynamic import. And we've added a new asynchronous task, something that takes time, but we've not informed Ember that it's happening. So when we say await visit this route, it's waiting for a settled state, which happens when the render phase is completed. But there's still stuff happening. The DOM hasn't truly settled until that highlighter is applied. But the test asks the question too soon, and we get a failing test. Now, the solution is actually quite simple. So I mentioned Ember test waiters earlier. It provides a method called waitForPromise. What we're going to do is we're going to take this chunk of asynchronous work, and we're going to wrap it to a call to waitForPromise. And this sets up the global, the settled state notification, if you like. So now our test passes, and it's still a slow test. It's taking about half a second. And I just want to drive this home by making this a really long wait. We're going to wait 5 seconds. So now it's a really slow test, but it should pass. And it does. So we've made life really difficult for ourselves. We made it so that the test was failing, and I'm now satisfied that this test is no longer flaky. And at this point, I think it's absolutely fine to remove the delay. And here's the visualization of that. So now when we do waitForPromise and load the scripts, we are actually informing Ember that we're in an unsettled state until it's complete. So that's my example of a test that may become flaky because of timing issues. Next, let's look at leaky state. We're going to start here by looking at the tests. Okay, so we've got 3 tests. One of them fails. I can run them again. Oh, they're all passing. Oh, one of them's failing. And they're all passing. Okay, we seem to be flip-flopping here. Now, the reason this is happening, actually, Qunit has a feature that's enabled by default, a configuration option. When this is enabled, essentially, Qunit pays attention to which tests failed, and then on the next run, it hoists them to the top of the list. It runs them early, so you get a quicker feedback cycle, which is pretty useful most of the time. But in this case, we seem to have an issue that depends on the order the tests are run. So I'm going to open up my test helper, and I'm just going to set that configuration option to false. And now when we run this, it runs in the same order every time, and test 3 is the one that always fails. Okay, so we've gone from a flaky test to a failing test, and now we can diagnose the problem and fix it. But before we do that, I do just want to mention one other configuration option in Qunit, which is seed. When this is enabled, it randomizes the order that the tests run in. And in my test helper, I've got these few lines here, which just add a piece of UI to the test runner in the browser. And there it is, randomize. We've got a checkbox. The tooltip, you probably can't read it, says, when checked, tests run in a random order. So let's try that. I don't know if you can see that, but there is a query param called seed. And each time I run this, they run in a different order selected at random. And if I keep doing this, if you pay attention to test 3, where it runs in the sequence, and whether it passes or fails, you're going to notice a pattern. There's only 3 tests, so there's not actually that many permutations here. Let me show you. There's 6 possible orders, and 4 out of those 6 cause test 3 to fail, and 2 out of those 6 cause it to pass. And the common thing to the 2 where it passes are that test 3 is running first. So it seems like test 3 is somehow influenced by the order that the tests are running. Let's have a look at the code. Okay, so in each test, we're visiting a route, and then we are making an assertion about a variable. And that variable is called my global variable. So that's the problem right there. Using global variables is frowned upon, and this is one of the reasons why. So I'm just asking you to suspend your disbelief for a little bit longer. I need to do this to prove a point. So in test 3, we're asserting that this variable is undefined. Let's have a look at the source for each of these routes. So we've got route 1 sets the value of that global variable. Route 2 also sets the value of that global variable. And route 3 doesn't set the value of that global variable. So, this is kind of a visualization of what's happening here. In test 1, we're writing this global variable, and then we're reading it, and we're getting the thing that we expect. Test 2 is the same. We set the value, and then we get the value, and it is the thing that we expect. But in test 3, we're not setting the value, we're only reading it. And so what we get back depends on what happened earlier. Now, one way we could fix this is we could say, okay, in route 3, we are going to just set that value to the thing that we're asserting on. And we do now have a passing test suite. Here's what we've done there. We've fixed the test. But I would say that we haven't really fixed the underlying cause here. We've treated the symptom, but we've not got to the underlying problem. The underlying problem is that this global variable outlives the lifetime of the tests. So a better solution, I would say, would be to somehow constrain the lifetime of that variable so that it doesn't outlive the tests. Let's just quickly undo those changes. We should be back to a failing test. Yep. And we could make this so by saying hook stop before each. I'm just going to set window dot my global variable equals undefined. And now the test suite passes. And I feel like that's a bit of an approximation of what I'm suggesting here, but the basic idea is do a bit of cleanup, make sure that state isn't leaking from one test to another. Now, I want to address the elephant in the room here, which is that I'm using a global variable. You shouldn't use global variables. But global state itself is not inherently bad. In a web application, there might be pieces of information that you need to know everywhere, like, is the current user authenticated? What's their preferred locale? What permissions do they have? What feature flags are enabled? Those are just a few examples I could think of. And in an Ember app, we've got lots of options. If you have global state, you might put it in a service. You probably won't put it in a global variable. But depending on the use case, you might want to put it in local storage or in session storage. And those are prone to leaking in the same way that a global variable can. So I've used a global variable here to illustrate my point, but whenever you're dealing with global state, you do have to be careful that you're not polluting the global namespace. I kind of think of an analogy for this, like in a professional kitchen. If you were slicing raw meat with a knife on a chopping board, and then you put that, and then you start slicing a tomato on the same board with the same knife, even if your chef is on the other side of the room, looking in the other direction, he's got eyes on the back of his head, he's going to scream at you from the other side of the room. Like, cross-contamination is a serious issue in kitchens. It can lead to food poisoning. And I think as developers, we need to treat global state with that same sort of sense of, it's good hygiene, So here I've done what I think is the simplest example that gets these tests passing. But more generally, as a general solution for this, I like an add-on from CrowdStrike called Ember Browser Services. I used this long before I joined CrowdStrike, by the way. I'm not just pimping it because I work at CrowdStrike. The idea here is that instead of reaching directly for the browser window, you would reach for the window service. And in your production environment, it's pretty much just an alias. You're still going to get the real browser window. But you can set it up so that in your testing environment, when you ask for the window service, it gives you back a mock. And under the hood, this is going to be doing something like before each to make sure that its lifetime is constrained to the test. So I don't want to spend longer on that, but I just think using something like Ember Browser Service is kind of good hygiene, good practice. So I started out by setting this scenario where you're working on a feature, you're under pressure, you've got a deadline, and then a flaky test appears at just the wrong moment and kind of derails your productivity. And in that scenario, I think it's okay to skip the test. I would say that the tests in your test suite aren't entitled to be run on circles on continuous integration every time. They have to earn their place in your test suite. As long as you make a pledge that you will go back and investigate that issue later, you don't need to fix the flaky test right now. But when you've got a flaky test, it tells you that there is smoke. And when you skip the flaky test, all you're doing really is concealing the smoke. There's still fire. And if you leave that fire to burn, it might grow, and you might find that smoke starts appearing in other places. We looked at another solution where essentially we fixed the symptom, but we didn't treat the underlying cause. And I mean, to be fair, it's hard to know whether you're treating the symptom or the cause. Sometimes it's hard. But this solution is, in some ways, it's just as pernicious as skipping the test because you've concealed the smoke, that there is still fire, and again, that fire might grow and you might start seeing smoke elsewhere. The best solution, really, is if you can find the root cause and fix that root cause. It might be that you have 5 tests that are flaking all on their own interval. And when you fix the root cause, suddenly all 5 of those flaky tests are fixed in one fell swoop. I think there's a temptation when you see that you have a flaky test in it's failing in continuous integration. You want to run and git blame. You want to find out who wrote that test and ask them to fix it. But I think it's important to understand that that test may not be the only bad actor. It may not be the source of the problem. Really, when you have a flaky test like that, it's sending you a vital signal, which is that you have a problem. And the sooner you know that you have a problem, the sooner you can fix that problem. So don't blame the flaky test. You should thank the flaky test. And that's all I've got.